Hey everybody, this is Mr. Kane again, and this is the beam deflection Google Sheets model part 2. In the first part, we set up our tables here. So you should have this title, and you should have these 3 separate tables for the 3 phases of testing. You should have them color-coded in terms of just formatting. These colors just are used to separate, like green for phase 1, blue for phase 2, and red for phase 3. As I noted before, these cells that I've painted in yellow are just ones that are simple data input, data entry, and the ones that are in green for the green table, blue for the blue table, and red for the red table are calculations. And you can see that when you click on each one of these cells and go up here, you can see it says equals, and then there's an equation. That means it's using these other data cells to calculate the answer. Okay? So in this video, it's just going to be a short one. We're just basically going to show you how to do a few of these calculations, and then you'll finish it off on your own. So the first one is the moment of inertia. And again, from watching the video, you'll know that this is the equation for this is going to be B, which down here we've shown you moment of inertia calculation, B, which is the beam width, times the height of the beam cubed divided by 12. So all you would need to do in here, if I hit delete, I can just say, I can hit the equal sign, and then I can just simply click on the beam width, and then I can do asterisk, which is the multiplication symbol in Google Sheets, and then I can click on the height, and then I can use the caret here to the third power, and then divide that by 12, and hit return. Okay, and there's my answer. Then we want to come over here, and we can calculate the max beam deflection, which is just simply the measurements from the ground that we took. And we're just going to subtract one from the other because that's obviously how far the beam was deflected. So we can just hit again, we can hit on our keyboard the equal sign. We can click on the preload distance, hit the minus button, and then click on the post-load distance, and then hit return. And it sunk 1.3 inches. And then we want to come over here and calculate the modulus of elasticity. This is the property of the material itself. It is not a function of the orientation. It's a function of what the material is. And again, you should have watched that video that I posted that talks about the modulus of elasticity. It's the slope of the stress strain curve. So how much a material will strain or deform based on how much stress you put on that. So wood, will have a higher elastic modulus than, say, plastic will. Okay, and so it just is a representation of how strong the material is to deformation. And if we look here, we're going to see down here the modulus of elasticity, E, we can see our equation. Okay, the force that's applied to a beam of a certain length divided by 48 times the moment of inertia times the beam deflection. Okay, and if we come up here, I'm just gonna start to enter these numbers. So I'll hit, I'll get rid of what I had in there, hit our equal sign, okay? And I'm gonna start using some parentheses here. Sometimes you need to do that for order of operation. So the first one is going to be the load. As we come down here, you can see here, F is our first term. So I would click on the force applied, and then I'm going to, you can see here, I'm putting the length to the third power. So I can just click on my length in inches. Okay, we need to have that span in inches because the modulus of elasticity is PSI, or pounds per square inch. So our units have to match up. So I can just click, we'll come back up here to where we are. So we'll click on span, and then I can use my shortcut terminology to cube it, okay? And then I can end my parentheses and divide it by, type in 48. Okay, we're going to multiply it times our moment of inertia, so I'm just going to click on that. And then I'm going to click on my max beam deflection. Okay, and parentheses, hit return, and there we go. All right, now you'll be expected to come down here and do that for each of these. For the blue table, you should be able to calculate the moment of inertia for each of the blue and red tables. And then as you come over into the blue table, you can certainly calculate the max beam deflection. And then based on your lab and by, moving terms around on your different equations, you can see that you can calculate the load. So if you have the moment of elasticity, or excuse me, the modulus of elasticity, you can see here that you can solve for other terms like force, okay? And the modulus of elasticity, again, from your video that you watched, is an inherent property. So because in this blue table, we're using the same beam as the first one, it's the exact same beam, it's going to have the same modulus elasticity. So what I did here was I just said equals J8. So I could say, I could hit delete, and then I can just say equals and click on this cell up here and hit return. What that's saying is, hey, I've got the exact same, whatever I calculate here for this beam, it's going to be the same one for the second phase of the testing. You should be able to use the modulus elasticity, the moment of inertia calculated, to calculate the force of the person, okay? So that's just showing you that once you know the modulus of elasticity, you can do an experiment and put someone or some type of weight on a beam, measure the deflection, and then you can determine from that how much the person weighs or how much that object weighs, how much force, pound force they're exerting on that beam. Okay? And the third one is where we're assuming person two, this person that weight you calculated, okay? And you can see here what I did when I click on their weight. That's an input. It's going to be the weight of that person you calculated before. Let's say we take that beam and where we had it flat, we're going to stand it up on edge now, which is actually in construction how you would always position a floor joist or a roof rafter up on edge where it's the strongest to a vertical load. And that's why this moment of inertia calculation is much higher than before, because moment of inertia is a function of the orientation of the beam. So when we put the 2x4 up on edge where it's tall now and put a load on that beam now, it's going to have a much higher moment of inertia, okay? And so what your job is to, what we're going to do is we're going to be able to calculate the deflection of the beam. So this is really kind of what you would do in a real structural engineering job. You would know the modulus of elasticity of typical construction materials. You would know how much load you want to put on that beam for the design of the building or the structure, and you would calculate the max beam deflection and see if that's within bounds of your design. If this max beam deflection gets too big, you would start cracking your joists. You could start cracking drywall. The structure could fail. And so this is kind of like your final phase of design. So I'm going to leave it up to you to calculate these other variables here that are in blue or red. Okay. So this is going to be the end of part 2. In part 3, we're going to go on to this, where we're going to be able to just take a particular case, which is spelled out right here, and we're going to plot up these 2x6s and 2x8s and 2x10s and lay them flat or vertical and calculate these different deflections and plot them on a curve. Okay, but that'll be for part 3. So good luck.